Okay, welcome to part 2 of day 10 of Advent of Code 2023. So the last one took a very long time to implement for me. It was just a lot of repeating the same stuff, going over all the different combinations of things quite slowly to make sure we get it right. So we're on to part 2. Now part 2 essentially takes everything from part 1 but then adds a layer to it. So what we need to do is if we found a path in part 1, we then need to determine how many squares, how many dots are inside the entire loop. Now, if we've got all of these here, all of these zeros are not inside the loop, only these i's are. However, if we take out the zeros in the middle here, we're then left with no gap. Still, this is the same thing. We have a larger example here where, as you can see, there's a lot more space, and we've got all of these zeros all the way around, and then we just have these few i's in the middle here. So these are the only ones that we're actually counting. This one here, these few here, and this one. So there's 8 tiles enclosed by the loop there. Finally, we then have this bigger map, and this time we just have these for a number of eyes, 10 eyes enclosed by the map. We need to figure out how many, figure out whether you have time to search for the nest by calculating the area within the loop, how many tiles are enclosed by the loop. So this one, initially I thought was going to be extremely hard. And then I come across a very simple idea that given any polygon, you can draw a line from wherever you are to the edge of, the whole map, the whole area. And depending on how many lines of the polygon you cross, you can then determine if you're in or outside of the polygon. Now we've got some weird edge cases here with the corners and all that kind of stuff, and where it goes from, say, an F across into a horizontal pipe, and then a J to go up. So you've got, technically you're actually only crossing 1, but you're actually crossing 3, and then obviously you can increase the amount of horizontal pipes there to 10, 50, 100, but you're still only counting 1. You're not counting however many there are. So this one is quite a annoying problem to solve if you don't have that kind of prerequisite idea. Now I'm just going to take everything from part 1 firstly, because essentially part 2 needs all of part 1 to be able to work. So I'm just going to select everything, yank that, go to part 2, and if I just paste it down here instead, because then I can get rid of solve, and if I then just grab all of this, delete that, and instead paste it here, and then just get rid of all of this. We don't need that. Okay, so we have the test solve. Oh, we don't need that either. Great, cool. So now we're back to here. For this particular one, I was just using the this example that they've given here, and they're going to try and get to 10. So now we have this value. Let's fill it in. So let's say solve with the test input is equal to 10. We could do these other ones. So for example, we could do this one with 8. We could do this one with 4, just to give us some other scenarios, but I'm just going to keep it simple for now and just do the biggest, most complex one as a test. Okay, so for this one, we essentially still need to get all of the different positions, move around the grid, but this time, instead of just getting the position, we also want to store it in a set. So to start with, if we so we want to do it here, I think. So let's say scene is equal to set. So we still get the same start position. We still process it in the same way. So if we get the I was trying to think of what I did before. Right, so we have a scene set, and then essentially we want to move around the entire grid, get the entire or determine what the actual start is first, because we need to actually fill that in. So if we very quickly do that, so we don't need the scene set for this, so let's just do it before we start on all of that. So we've got the start position, so then we say start paths is equal to get possible what do I call it? Get next position. We're going to give it the grid. We're going to give it the start position, and we are going to give it the previous position. This time, though, we are going to need to return multiple, because we do want the different positions. So if we give it this time, it's going to return a list. In fact, yeah, it's going to return a list. So if it's an S, we're going to return. We are going to want now to append the positions rather than just returning one. We are going to want multiple. So paths paths is equal to list, and then we'll say paths dot append new position. So let's just yank this. Let's paste it in there. Yank. Paste it in there. Yank. And paste it in there. And then we just want to return paths. So if I change this now to be a union of a list of tuple of int or a tuple of int. That's very messy typing, but never mind. So we're going to return the tuple there. We need to import union up here. Return type of list tuple int or a tuple of int. Yeah, that's right. Function declared with this must return a value on all code paths. None cannot be assigned to type. Blah blah blah. Oh, okay. Fair enough. So it's just because we've got all these different ifs, so let's just return return a list down here. Cool, there we go. So if it's an S, we're going to return all the paths. Otherwise, we're going to be doing the whole direction thing again. Let's just double check what this is saying. Return statement outside of a function. Like that. Well, that should be alright. Oh yes, we got this up here. Cool. So we know that the next position is going to be a tuple there. So I think this is really just a cannot be assigned to type tuple or none. We're not getting none. I don't see that as a problem. Anyways, right, so we have the start paths here. So what we want from here then is to say the start character is equal to none. So if start paths 0 and so we've got the first path and the row adjustment is equal to start paths 1 0, then start C is equal to horizontal if start paths 0, 0 is equal to 0, else it is going to be a pipe. Left start paths. So this one has, at least for me, has so much of this kind of logic all built in to this this problem. This one took me a long while to figure out all of this stuff. Start paths 1, 0. Then, so if the paths, if the first one is less than the second one, then we're going to be going in a particular direction. So we want start C is equal to L if start paths 0, 0 is equal to 1, else J. Get possible paths. Sorry, get next position. So that's actually giving us the new position, not the adjustment. So if the path is equal to 1, it's not necessarily right, I don't think. Let's go with it. Okay, so else J. So then we have just the final else. Start C is equal to F if start paths 0, 1 is equal to 1, else 7. Cool. So then let's just do assert start column is not none, just to make sure that we're actually setting something. Method not defined on type int. Get item method not determined on int. Yeah, but we've got an S to start with, so we should be good. Right, 2. Current character is grid position, start position. List indices must be integers or slices, not a tuple. And that is line 48. Oh yeah, get next position So that's at one point going to return. Yeah, it's going to return a thingy, isn't it? Okay, so next positions we have paths is all of this. If this, return paths. Okay, so then let's just do. So we want to replace this whole line. Is it colon S? We want to replace return. Do I need /? Yeah, return new pos. I want to replace that with paths.append new pos. And I want to do it globally. Yeah, so just that. Cool. How do we repeat the last substitution? I can't remember. Okay, so let's just do a. If I just select all of that, then do substitute return new pos for paths dot append new position. Boom. Excellent. So then we want to just do return paths. So then, because we're now returning the paths, up here we can just say next position is this. Positions is this. Start position is next pos 0. And then this will always, this will then always return like this. Always return a list. Cool. Nice one. Okay, so let's just give that another go. Yeah, so this is now running through. We are getting the start character set correctly, which is nice. Excellent. Okay, so then what we want to do is essentially go over everything we did before, but instead of just moving on, what we want to do is set the or add the previous position to the scene set. So scene dot add prev position. We do this, we carry on, we don't care about a total anymore, and that gives us all of the grid that we're looking for. So after we have all of the not the grid, the path, that has all of the path. So now what we want to do is go for row, so for R row in enumerate grid. For column in range 0 to the length of the row. So we could just do to the length of the row. I don't think we need 0 in there. If row column in scene, we are then just going to continue, because that's part of our path pipeline. So instead, what we want to do is we want to count how many pieces we meet if we just go straight to the left, or up, or right, or down, or at a diagonal. Doesn't really matter. Diagonal is probably even harder, but to the left or to the right, up or down. Same sort of premise. Just need to change up the characters that we're going to look for. So let's say count is equal to 0. For let's say the column, so this is the inner column, the inner loop column. In range we want to go up to the length of the row up to the column that we care about. So for the column up to the length of the row up to the column, that give us what we need. If we do column +1, that's the column +1. Let's do it that way. So for column in that range, if row column is in scene and row column is in this. So what we want to do here is we want to check for a L, a pipe, or a J. So the reason we're going to do this is because if we are going, for example, let's say that we trying to think of how to describe this. So essentially what we want is to counteract the directions that we could be going. Sorry, not counteract the directions we could be going. So we want to essentially count the left angle and the right angle as one thing solely. So if we have, for example, an L and a 7, and they're connected via the horizontal lines, we want to count one of them. We don't want to count both. If we have a J and a L, for example, and we're going horizontally, if we go through the J first, we're then in. If we go through the L, we're then out. So we've gone in, then out. That is two horizontal. So that is two lines that we're covering. Whereas if we're going over an L and a 7, potentially that's not the same thing. It is the same thing. It's the same vertical line that we're scaling, or that we're crossing over. So essentially we want to not include 7s if we're including Ls, and we want to not include Fs if we are including Js, essentially is what we're saying. So we're counting one of the angle that could be on a horizontal plane. So if it is in there, then we're just going to increment the count plus equals 1. So then what we're going to do is we're going to take the total, and we are going to only add to the total if we have a remainder of 1. So if this is a odd number, if we cross it an odd number of times. The reason we're going to do that is, say we are crossing, let's find this one. Let's make it quite simple. So say we're crossing from this point here and we're going to the left. If we cross one time, we cross one pipe. So we were inside the maze. If we were on this one here, we cross the pipe, we go into the maze. We cross the pipe, we go out of the maze. So this is an even number of crossings, and therefore we were outside of the maze. I can't remember the name of the theorem for this, but it's quite easily findable. Finding a point inside a polygon. Essentially we're just going to be doing that, checking to the left each time to see, does this point sit within inside the path, inside the pipe maze. If we cross an even number of times, we are outside. If we cross an odd number of times, we are inside. Essentially is what we're doing. So we're going to go total. So for this is for each of the columns in each row, total plus equals, we want to do an int of count percent 2 is equal to 1. So this is basically going to identify all of the odd numbers, and because we're saying identify the odd, that's going to return a boolean. We're then going to convert a boolean to true, boolean to an integer, which is going to give us 1. If it is odd, it's going to give us 0 if it's false. So adding 0 to the total doesn't change it. Adding 1 to the total increases it by 1. And then we are finally just going to return the total. So let's see if this worked. It did. Excellent. So this one was quite a fun puzzle, like I said. This one took me a very long time, an hour to go through the first one in video form, and another half an hour to go through this second part of this one. So this one was quite a hefty one. But it was a really good little puzzle. So there was day 10. stick around if you are enjoying these videos for day 11, when we go through cosmic expansion, which actually was a really fun problem. So yeah, thanks for watching.